thank John for inviting me. It's a great pleasure to be here to see some old friends. Since I'm butting right up against the colloquium, I overheard John tell Wojciech that if I run long, I'm going to be tarred and feathered. So I think I should get started. This is what I'm going to talk about is joint work with Gert Sander and Jim Lawrence of George Mason plays a role as well, and he'll show up at some point in the talk. What I'd like to do to describe the basic problem, the basic thing we're looking at, is to think about a very simple example of linear time invariant filters, which are canonically modeled as convolution operators. So it's well known that if you have a convolution operator or a channel modeled by such an operator, in order to determine the characteristics of the channel, you send through a delta. And of course, if you do that, what comes out the other end is the impulse response, and then you know everything there is to know about this channel. So what I'd like to think of is think of the whole class of convolution operators, or a large class of convolution operators. So I have this class, and I have a single input, namely the delta, such that with the following property, that if I have two different convolution operators, I can distinguish them by examining their response to the delta input. So another way to put this is to say that I can define a mapping on this class of operators that maps an operator h to h of delta, the vector h of delta, and I want that mapping to be injective. But what I'd like to ask is a little bit more than that. I would like the mapping not only to be injective, but to have a bounded inverse, to be bounded and have a bounded inverse as well. Okay, and I would also like to have a way to easily recover the operator completely from the output of this delta. So in this case, it's completely trivial, and in that case, well, it's not so clear. So I'm leaving it a little vague. Okay, I'll be more specific at the end. So the problem that Gert's got me interested in, or invited me to participate in, I should say, is doing the same thing for linear time variant filters. So we take the same formula as before, but pop in an x on the h, and we have a model for a communication channel that varies with time. What I want to do is take such an operator, and I'll be interested in three different representations. One is as an integral operator with kernel kappa. Okay, there's the relationship between kappa and the impulse response h. I also want to view h as a superposition of time and frequency translates, like this, and the weights that go on those time and frequency translates is referred to as the spreading function of h. And I also can view h as a pseudo-differential operator with symbol sigma, and you notice that the Fourier transform of sigma is essentially the spreading function. So the question I want to ask is, if I look at some large class of operators of this type, can I find a single input with a property that if I send that input through, I can determine whether I have two different channels or not. Okay, and I also want the stability criteria, and I'd also like to ask for a simple reconstruction formula. And this problem is called the problem of operator identification. And we would say that h is identified, or this class of operators, I should say, is identifiable with identifier f. To give a little bit of history on this problem, about 50 years ago, Kylaf considered the class of channels with maximum time spread A and Doppler spread B, and argued that for such a channel to be identifiable, it's necessary that AB, that the product of those two spreads, maximum spreads, be less than or equal to 1. So in our language, that would mean this would be operators whose spreading function is supported on this rectangle. The operator that he chose to do that is a delta train. And if you think about it, it sort of makes sense. Okay, if you send a delta through one of these channels, okay, since the time spread is limited to interval 0a, the response to that delta will die out after a time unit. So you wait, so you send your delta through, wait for the response to die, then send the next one through, wait for that response, send another one through. So in that sense, you're sort of sampling the channel with deltas. And the question is that enough information to completely recover the operator? And this was shown by Kotzek and Fander to be correct, so that this is a necessary and sufficient condition for that to be the case. And this idea of sending through trains of deltas is what we call operator sampling. Now, Kailath argued that this was true, and here's basically what his argument, basically what he argued. It doesn't look like this, but this is what he said. So, here's why this makes sense that you can do this. So let's suppose that our spreading function is supported in this unit square. Okay, so I'm going to say why it's identifiable in this case, and if it was any bigger, it wouldn't be. Then the kernel of the operator satisfies this relation. Okay, it's essentially the inverse transform of the spreading function with respect to the second variable. Okay, and if we think about what we know about the supported eta, what we can conclude about the kernel is that it's supported on a strip, slanted at a diagonal, and also that that for each t, this function is band limited to 0, 1. Okay, now if we send this delta train through our operator, this is what comes out. Okay, just the sum of kappa of x n. Okay, so let's look at a picture here. So this strip is so kappa is supported in this strip, and on every line of this type. So this is just an example. If we consider that line, if we restrict kappa to that line and consider it to be a function of x, this function is band limited with bandwidth 1. So therefore, we should be able to recover it as long as we have samples on at points that are 1 unit apart. So if we know kappa on this line at these points, okay, then we've recovered it on this line. So if we know it at all those points, then we can recover the kernel of the operator. Now, what's our data? Well, our data consists of samples of kappa at the integer. So we have we know it for all x's and for each n. Okay. Now here's where the support idea comes in. If I want, say, that point, okay, all I have to do is drop down to the x-axis, to this point x, and just read my data. Okay, because these lines are disjoint, if I project them down, the sum in the previous slide reduces to only 1 term for each x, so I can pick up these samples without any trouble. Okay. Now, if my bandwidth was bigger than 1, I'd have to oversample, so I'd have to take more of these horizontal lines, and then I'd get overlap. So for given x, I would have several terms in the sum. I couldn't separate them. Now, another way to look at this, I'll mention quickly, uses a tool from time frequency analysis, the Zach transform, which takes a function on R and produces a function on the unit square. Okay, it's essentially periodic. Okay, and it's also unitary on L2. And when we think about our operator sampling, this relationship is very easy to show. Okay, and using this, we can obtain an identity like this. So the Zach transform of my data is essentially a periodization of the spreading function. Now, so the observation here is that if eta is supported in the unit square, there's no aliasing error here. And so so this periodization completely determines eta. Okay, so that's another point of view on why we need that unit square. Okay. Now to take this a step further, okay, about 10 years after this, Bellow pointed out that it's that the important thing to look at on these time-varying filters is is not the product of the maximum time and frequency spread, but the actual size of the support of the spreading function. So that could be in pieces, okay, but as long as its total area, it's spread out all over the place, but as long as its total area is less than 1, he conjectured that that should be enough. Okay, and actually, Kylab pointed this out too. If you read the paper, you see that he's mentioning something like this. Okay, but Bellow pointed out again. And this is what Gertz and I were able to show was true. Okay, that if the support has area strictly smaller than 1, that class of operator is identifiable. Bigger than 1, it's not identifiable. Okay, so we can take a minute to explain our proof and the reasoning. It comes up later, so it's important that I do that. But just to show you why you can do this, let's make a couple of simplifying assumptions on the support of eta. First, we'll assume it's Jordan measurable, so we don't have a result for any sort of Lebesgue measurable set. But we'll assume this, okay? And we will also assume that the support is contained in this rectangle, 0, 1 cross 0, L, for some integer L. And if we divide this rectangle into subrectangles, into L squared subrectangles of shifts of 0 to 1 over L cross 0, 1, then we assume that the support of eta meets at most L of those rectangles. Okay? So forgetting about that for the moment, okay, let's think about what this means. Well, we look at our picture again. Okay, since the kernel restricted to this line is as band limit L now, or bandwidth L, we have to oversample. Okay, and of course, as we saw before, you can't do that without running into redundancies. Okay, so the trick. The simple trick is to just weight these samples, okay, with a periodic sequence. So in this case, L is 4. Okay, so we just weight it with the same weights on each group of 4 samples. Now we go back again to time frequency analysis, and we dip in and.
That's so it doesn't overlap when they come down?
I'm sorry. No, they do overlap. We can't avoid them. Yeah, so they do overlap. So yeah, so we're taking 4 samples per unit. Okay, and so they do overlap. So we have to find some way to unravel them. Okay, and so the idea is to just weight them with constants and see what happens. Okay, and so it always works. Otherwise, it would be described. But in order to see why it works, we'll take a short digression, one slide digression into Gauver analysis. So Gauver systems in finite-dimensional space, we can define for vectors in CL a translation operator that just does sort of a circular translation, and a modulation operator, which we just multiply the vector by powers of omega. Okay, and if we take all possible shifts and modulates of my vector C, okay, then I get L squared vectors in CL, and this system forms a frame for CL. Now, what do I do with that? Well, if I take that Zach transform formula that I had before and simply apply it, and I should point out that should be n over L, not n. And so I take the Zach transform of the response of my filter to this kind of delta train. Okay, what comes out is this. Okay, and what you notice, so let's ignore that. Okay, that's just a phase factor. So here's my spreading function, and here is what? These are coefficients in my finite Gauver frame. It just comes out just beautifully like that. All right, so the bottom line is that I can view my spreading function as, if I restrict to this rectangle, I can view my spreading function as coefficients in some attached to a collection of L-squared Gauver vectors in CL. Okay, so clearly in general, that's an underdetermined system, and I should not be able to recover eta from that, from those data. But we're saved by the fact that of the support of eta. There are only L non-zero terms here, okay? And so the resulting matrix is square. And now the question is that invertible? Is it always invertible? And well, that's a little harder than we thought. But in fact, it is true that you can, with an appropriate choice of a vector C, you can arrange it so that it is always, so that any submatrix is invertible. So any selection of L columns of that L by L squared matrix is invertible. Okay, so that does it. We are now able to recover eta completely from the data right there. Okay, so that's essentially the argument. Now, so I want to change gears a little bit. So that's sort of some of the work that we did a couple of years ago on the basic problem of identification. The question that comes up now that I want to talk about is what's the appropriate setting for doing this kind of operator sampling? I mentioned before that we look at a class of operators, and then there's a single identifier that can identify that whole class. And I talked about operator norms being equivalent to function space norms, but I didn't say what those operator spaces or function spaces were, and that turns out to be something that needs some work, requires some thinking about. So what is the appropriate setting? Now, one thing that we want to have, this is the main criteria that we look for, is that the setting should be broad enough to include some basic kinds of operators that we're interested in. So, for example, ordinary convolution operators. Okay, so the spreading function for such an operator is distribution. Looks like this. Okay, multiplication operators. So if h is just a multiplication, then the spreading function of h looks like this. Okay, and this, of course, would include the identity operator. So we'd like to have an operator class wide enough to say that if we have the identity, we should be able to identify it. So the identity would correspond to a distortion-free channel. So we'd like to be able to identify the identity. I might point out at this point that the original proofs of Kotzek and Fander, and also of Gertz and I later on of the Bellow conjecture, were in the setting of Hilbert-Schmidt operators, in which the spreading function was assumed to be smooth and in L2 at least, and so that actually did not include these examples. So we proved it was not in full generality. So to identify that appropriate setting, we once again turned to time frequency analysis and define the modulation spaces, which I think are probably familiar to 95% of you in the room, but that's okay. If we're given a function phi, we look at the short time Fourier transform, okay, which looks like this. The g should be a phi. That's a typo. I apologize. So we can define the short time Fourier transform, now a function of 2D variables. So this is an RD, 2D variables. And we define the modulation space MPQ of RD to be all those distributions whose short time Fourier transform sits in the mixed norm space LPQ. Now we can, of course, we can have weighted modulation spaces and things like that. We could go more general, but I thought at this, even the last talk, I wanted to limit the number of indices that are floating around. So that's, so we're just going to do this for the sake of the talk. M11 is the famous Feichinger algebra, and its dual M infinity infinity is the dual space S0 prime. And it turns out that S0 prime is sufficiently large, a sufficiently large class to eliminate all the examples that we're interested in. Okay? So with this in mind, we define so-called operator Paley-Wiener spaces on which we can do operator sampling. That's the sort of motivation for using that name. But if we're given a bounded Jordan domain S, we can define OPW PQ of S to be those operators where the support of the spreading function is an S, and the symbol sits in this space MPQ11. Okay, so you remember that the Fourier transform of the spreading function was essentially equal to the the symbol was essentially equal to the spreading function. So we can think of this class, the class of operators with band-limited symbols. Okay, so that's why this is a 1-1 in the frequency variable. Okay, but we can distinguish different classes of symbols in this way. Okay, so this is a Banach space with respect to this norm. And by choosing P and Q equal to infinity, okay, we include all of the types of operators that we're interested in. Okay, we do have to restrict our convolutions to compactly supported kernels and our multiplication operators to band-limited functions. Okay, at least now we have to do that, but it's still large enough. Okay, so I'm going to finish with a couple of the results in this direction. The first one is the most general one, where we basically do the bellow conjecture. So for arbitrary regions, with all the details put in, or most of them anyway. So suppose that P and Q are between 1 and infinity. Then the operator class OPW PQ of S is identifiable if the size of S is strictly less than 1, and not identifiable if it is larger than 1. In this case, we have this norm equivalence that the operator Paley-Wiener norm of H is equivalent to the MPQ norm of this output. Okay, so of course the C and the L must be chosen depending on the support. Okay, but certainly the identifier exists. Okay, and we have this norm equivalence. We also have a reconstruction formula, maybe a little complicated, but I can say that it looks something like this. Okay, so we recovered the impulse response through a formula like this. The RPQ and the SPQ, there should be a PQ there, again. They have nothing to do with the support. They're just basically partitions of unity, essentially supported on one of these small rectangles. Okay, these coefficients B, P, Q, K are they depend on PQ on the rectangle that we're looking at. They also depend on the geometry of the support of the spreading function. So they have to do with the inverse of that matrix, that Gauber matrix that showed up before. Okay, so essentially the data about what the support of the spreading function looks like is contained in these coefficients, and also in the delta train right here. Okay, but we get something like that as a reconstruction formula. Now, going a little bit less detailed. Okay, if we look at the situation in which the support is a rectangle. Okay, we have this result. Okay, this is the Kotsek family. Okay, and again we have the same type of norm equivalence. Okay, and we have but the reconstruction formula is considerably simpler in this case. Okay, and it starts to remind you of of something from, say, classical sampling or something like that. And that's what I would like to finish with. If we assume that our operator is a multiplication operator with a band-limited symbol, and we just directly apply this theorem, don't do anything fancy, a sampling result exactly like this. Okay, so I've changed the A's and B's around a little bit, but this is exactly what we have. So band limited, the function band limited to minus omega over 2 to omega over 2. Okay, and we recovered where if omega times t is strictly less than 1, we have this sampling formula and we have this norm equivalence. So this is a direct application of that previous theorem. That is the last slide. But what I wanted to mention is just sort of where we're thinking of going with this. So what this does is it identifies operator sampling as a generalization of classical sampling. But if you just think about even the stuff that I mentioned in the talk, there are some significant differences. Namely, one of them, obviously, is that if you look at the class of operators with band-limited symbols, there's an absolute maximum on the size of the bandwidth, or the size of the spectrum, which will allow for sampling. If it's too big, no amount of oversampling will compensate. Okay, so that's not true with classical sampling of band-limited functions. If you have a bigger bandwidth, you just sample more. Another difference is that, at least a superficial one, is that with operator sampling, when you do have to oversample, it seems that all you need to do is attach weights to your samples, and you can get away with it. You can actually unravel these extra samples, but that's not something that really works with classical sampling. If you attach weights to your samples, it doesn't really make any difference if the weights are non-zero or all non-zero. So kind of where we are is exploring, what can we do with this? Is there, can we do irregular sampling, something like irregular sampling of operators, and what would that look like? And just sort of trying to think about that, and can we get the reconstruction formulas for the irregular case, and so forth. So anyway, that's kind of where this is at the moment. So that's all. So thank you very much.
Despite what Dave said earlier, I know better than to mess with numbers when I get them. Would you like 1 more minute, maybe? Are there any questions? Well, if not, then we thank the speaker again. Again at 3 o'clock in 15 minutes.
Well, but before you leave, I would like us to thank the organizers for a couple of really wonderful sessions.